Welcome everybody to the fifth part of week 1 in the Parallel Programming Concepts course at OpenHPI. My name is Peter Tröger. Today we want to talk about memory architectures. So we want to have a look into how memory is attached to modern processor and computer technology to get an idea of how to deal with that when we start to go into parallel programming problems. One way of describing the different levels of hardware parallelism we may be able to exploit is this picture. So we already talked about the differentiation between multiple cores per processor, chip multiprocessing, or other ideas of how to get parallel hardware inside the system. Parallelism on different levels starts on the smallest, on the lowest level, where we have actually one processing element, one piece of hardware, one core that allows us to run instructions, and now we take our program and divide it into multiple tasks, and these tasks are then enabled to run on this processing element. Here, mechanisms such as ILP may already kick in that allow you to speed up the execution. Otherwise, the concurrency features of the operating system will allow you to run all these tasks in a concurrent fashion on the processing element. The second way of having parallelism in hardware in a particular system is to have multiple processing elements, cores or processors, in one machine. And all these cores and processors share the same main memory. That's a common principle you can find when you buy a modern machine. So each modern laptop has one processor, and this processor has multiple cores. Each of these cores forms a particular processing element, and all of the cores can access the same main memory. Even if you have an SMP system with symmetric multiprocessing, meaning that you have multiple processor chips inside the system, then all of these chips still can access the same memory, so this still belongs to this class of parallelism. The third idea would be to have a system where you combine multiple machines or nodes by a network technology in order to cooperate with each other. In this case, all of the nodes have their own local memory, so you no longer have the situation that they share the same memory resource, but they have their local memory and otherwise have to collaborate with the other participants by the network capabilities. So the typical categorization of these parallel hardware levels from a memory perspective is the distinguishing between shared memory systems and shared nothing systems. So parallel processing hardware organized as a shared memory system means that the processing elements all share common main memory, which means that all of the tasks can theoretically access the same kind of memory, the same kind of data that is stored in this memory. When we take the example of tasks as being mapped to threads as execution units, we have the situation that all the threads can access the same address space inside the operating system. It's one operating system process. You have multiple threads as execution units, and the tasks now running inside the threads, and they can access global variables and other kind of global data. Shared memory systems today, shared memory hardware, is typically implemented with a hierarchy of caching levels. We saw that in earlier units, how caching works in modern systems and how that helps to get a faster speed in the software execution. This is an effect that must be considered if you try to optimize parallel software for the maximum speed up in the computation. Besides shared memory systems, we have the other class of parallel hardware setups, which is called shared nothing systems. In a shared nothing system, we have the situation that tasks are mapped against the execution unit, but these tasks and execution units have only local memory per node. And all these nodes together form one parallel piece of hardware, but since you no longer have a shared memory between all the nodes and all the processing elements, we have the situation that we need another way to perform synchronization or communication between the activities that run in parallel. This is typically done by some kind of messaging approach. So you have the ability to exchange messages between the processing elements instead of accessing the same global memory from all the processing elements itself. When you have these two approaches, they can be seen as completely distinguished classes, but the more typical situation today is that you have hybrid setups of parallel hardware. So you have shared memory systems with multiple cores or even multiple processors. They form a machine, and these machines are now combined into a larger computational cluster in order to perform in order to run some parallel software. So you can see this as a way of how this general classification then maps to reality by having intermixed systems. Another example is accelerator hardware. So if you have a GPU card inside your system that you try to use for speeding up your software, then you have the situation that the GPU card has its own local memory, and the main system has its cores and its CPUs also attached to main memory. There are ways to exchange data between the card and the main memory, maybe even by direct access, but the typical situation here is that you have no longer this equal access to the same kind of memory with the same latency and the same speed. Shared memory and shared nothing systems is again a well-known classification for a long time, so this is nothing new. The problem with these terms is that they are not used in the same way everywhere in the literature. So this slide tries to give you an idea how other people call this distinguishing. So for example, when you look into Feister's book, then you find the term shared memory versus distributed memory, mentioning the fact that the memory in a shared nothing or distributed memory system is no longer at one place, but spread it over different local nodes. Ian Foster calls it multiprocessor versus multi-computer, talking more about the way of how processors are interconnected and how they work with each other. And Tannenbaum calls it shared memory versus private memory in his book. So whatever the terminology is, the overall principle is always that you either have a system where the processing elements can access the same memory by direct addressing, or you have a system where the processing elements need to exchange messages in order to coordinate their tasks. Let's talk about shared memory systems. Shared memory systems with their global address space can be further distinguished into two categories basically. One is uniform memory access systems, UMA. In these systems you have the hardware promise or the hardware situation that all processing elements have an equal access time to the main memory. This means that when you write your parallel program, if you try to do your parallelization in the code, you actually can rely on the fact that whatever variable you access, whatever kind of data you access, it doesn't matter where this data lives. You can just access it by the variable name or maybe by a pointer, by an address, and then you get this, roughly the same speed of access when we ignore the caching aspect. From a hardware perspective, the alternative approach is a so-called NUMA system, non-uniform memory access system. In these systems, we have the situation that the access to a particular piece of data in the shared memory may take a little bit longer or less longer, depending on the fact where in the address space this data is located. We will see in a moment why this is the case. And this is a situation that were mainly relevant for high-performance computing and supercomputers in the past, but which becomes now relevant and crucial for modern computer systems, even with standard processors and with standard use cases. So NUMA is a concept that is known to a few experts for a long time, but which is now a mainstream problem that more and more becomes relevant due to memory hierarchy effects. And for NUMA systems, there is a special class of systems called CC-NUMA, cache-coherent NUMA. This is what you find in modern SMP systems with multiple standard processors. So you have a NUMA system where the hardware takes care of the fact that all the caches on the different NUMA nodes work consistently with each other. So this is a transparent mechanism that eases the implementation of your software. There are some research ideas of building systems, NUMA systems that are no longer cache coherent, which brings more burden to the software part, but this is something that is not well proven in practice, so currently we're still sticking with the CC-NUMA approach in modern parallel hardware. Okay, let's have a look into a UMA example, uniform memory architecture example. Here we have an example of a system with two sockets, meaning two processor chips. Each of the processor chips has two cores. So we have a dual core processor and an SMP system built from 2 dual core processors. Each of the cores has a level 1 cache, which is the smallest, fastest version of a cache directly attached to the core. And then we have a commonly shared level 2 cache between the 2 cores. Both sockets, both processors are connected to the memory controller and the chipset via a system bus. And the chipset and the memory controller now controls all the memory banks and the memory modules we have inside the system. The relevant aspect is here that regardless of the fact where a particular task and its execution unit is running, the access time to the main memory is always the same. So it doesn't matter on which core the particular thread or process is running, it can always access main memory data at the same speed. The caching may further improve the particular performance of the data access, but from a memory access time perspective, we have always equal conditions. So from a scheduling point of view, it doesn't matter where you put the different tasks, as long as you find an empty core that still allows you to run some work on it. The counter example or the other example for NUMA then is this picture. Here we have an example with, again, 2 processors, 2 sockets, but in each of these sockets we now have a 4-core processor. So we have 4 cores per chip, and each of the cores again has some caching hierarchy and an internal memory controller. So the big difference that we have with modern processor technology is that now the memory controller lives inside the processor, at least in part, sometimes completely, and the memory modules are now directly attached to the socket and the processor chip. This leads to the fact that now we have somehow a distinguishing between one part and the other part of the memory, but the software running in the system still wants to have the notion of a shared memory system. So if you run a parallel application using 8 cores, you still want to have one address space that, for example, is accessible by all your threads. So how does the hardware solve that problem? It solves it by giving you the illusion of a common memory address space based on a chip interconnect technology. So whenever one of the cores is accessing memory, it either accesses its own memory attached to the own socket, or it accesses the memory attached to the other socket or other sockets in the system. And the hardware transparently performs this memory access over the chip interconnect in order to deal with the other memory module. This is a nice approach as long as it's transparent, so you don't have to consider this in your hardware, but it leads to the effect that the access time for working with memory that is attached to other sockets is a little bit longer than the access time to memory regions that you have in your own memory attached to your own socket. That's one example for the NUMA problem. So we have a non-uniform behavior in the memory access times. This problem or this idea does not only hold for processor technology with multiple processors, but you can also take this to a larger scale, for example, when you have compute clusters in data centers. So the NUMA idea here again is that if a particular processing element, such as a core, is accessing memory, it depends on the region, whether it's located in one of the RAM modules or in the others. Practical example from real life, what you can see in this picture here is a 4-way Intel-Nehalem SMP system. So what do we have here? We have symmetric multiprocessing SMP, meaning that we have 4 processors. Each of the processors has local memory, its own memory controller, and its own level 3 cache, and something that is called QPI. QPI is an Intel trademark for Quick Path Interconnect, and this is the hardware technology that allows all the processors in one system to communicate with each other. On each of these processors we have 4 cores, and the cores share the global address space that is built from all the memory modules inside the computer. So whenever one of these cores tries to access a particular memory region, it depends on the fact wherever this is a region that lays in the local memory bank attached directly to the processor socket, or if it's somewhere else. In this case, QPI must be used to access data in other memory regions. NUMA is an effect that can be ignored in parallel programming and in software optimization, but if you want to have the ultimate performance and the best possible speed, it may be easier to actually, or it may be helpful to exploit the NUMA knowledge of the system in order to, for example, arrange data at the right positions or to work in a smarter way with caching. Beside this shared memory idea and the distinguishing between UMA and NUMA, we also have shared nothing systems. And as I said, shared nothing systems have the idea of no longer sharing a common global memory. So you may have local memories on each of the nodes participating in a shared nothing system, but from a global perspective, there is no longer a global address space. The most prominent example for such shared nothing systems are clusters, cluster computing. Cluster computing originally was the idea of taking machines and combining them with comparatively cheap interconnect technology. And by this you can either have something that is called a compute cluster, which allows you to speed up computation of a particular problem or application by using all the machines in parallel. Or you have something that is called a load balancing cluster, which does not give you faster processing of the application, but actually a better throughput. Another use case for clusters beside speeding up applications and making them faster is high availability clusters, where you can do failover mechanisms or fault tolerance mechanisms in your cluster. If you drive the cluster idea or the shared nothing idea to the extreme, then you end up with something that we call high performance computing, HPC, where you have massively parallel hardware, hundreds of thousands of cores combined in a multi-layer system that are used to solve the largest and biggest computational problems we have. Examples here are climate predictions, weather predictions, any kind of simulations from biological or physical processes. So this is basically the shared nothing idea with as many resources as possible and multiple levels in the memory hierarchy. So when we go back to our generic picture of tasks and processing elements, a cluster is basically a connection of processing elements with local data, local memory, and a messaging concept in between. And this can be built from your own components or can be built from comparatively cheap components, and is a typical standard way today for building large scalable systems that allow you to process a huge amount of data or to perform a huge amount of computation. A more specific or more detailed shared nothing example can be seen on this slide. If we take several machines with their own internal level of shared memory parallelism, we can now use them, combine them with an interconnection network and with a network interface, and this gives these machines the capability to exchange messages, and this allows you to use more cores at the same time. So you can run more tasks if you have them available in your application in order to speed up the application. And the addition of new machines is comparatively easy here. So one of the big advantages of shared nothing in comparison to shared memory approaches is that in shared nothing you simply have to attach a new machine, a new node to the given interconnection network. This is mostly much more easy than adding more and more processors and processor sockets in a shared memory system. So the so-called scaling capabilities are mainly given when you start to use shared nothing approaches, while scaling shared memory systems is a harder issue because you have to deal with the hardware issues that come from the global access from all the participating processing elements to the main memory. You can drive this example even further and can use a hybrid example where you take different machines with their own level of parallelism and then start to connect them by the interconnection network. So here you get a mixture of all the different concepts in one parallel hardware setup, and now you have to exploit this based on your software.